Once again, we're doing Advent of Code, a series of programming challenges that are published every year in December, with 2 challenges per day leading up to Christmas. It's a total of 50, and we've already done 3 of them in the previous video, so today we're going to look at Day 2, Part 2. As always, the website says that these challenges can be solved in any programming language you like, so I'm doing it in Funciton, an esoteric programming language that I invented some time ago, which consists of these boxes and lines which are created using Unicode box drawing characters. To recap, in the previous challenge we were given a text file with lines of text like these, where numbers are separated with spaces, and we were supposed to count how many of these are safe according to a criterion that is described here. If they're all decreasing or all increasing, then it's fine. But if there is an increase of too much, like 2 to 7 is 5, then it's not safe. And the maximum allowed is 3. So as soon as you have a decrease of 4, then it's not safe. Now the solution that we wrote last time looks like this. And the way it works is that it splits the input file at the new lines, obviously, so we get lines of text. And then we filter them by this single humongous criterion. And in order to evaluate the criterion, we need to split each line by the spaces, which is character number 32. And then we wrote this function which looks at consecutive pairs within the sequence. And we did a subtraction so that we have the differences between each consecutive pairs. And then we used these 2 criteria here to check for the differences. So we wanted the difference to either be between -4 and 0, which means that it's always decreasing but never by too much, or it is between 0 and 4, which means that it's always increasing but never by too much. And these limits are exclusive, so this is greater than 0 and less than 4. And as before, I'm going in completely blind. I don't know what the second challenge on this day is, so let's take a look at it now. Part 2. The engineers are surprised by the low number of safe reports until they realize they forgot to tell you about the problem dampener. The problem dampener is a reactor-mounted module that lets the reactor safety systems tolerate a single bad level in what would otherwise be a safe report. It's like the bad level never happened. Now, the same rules apply as before, except if removing a single level from an unsafe report would make it safe, the report instead counts as safe. More of the above examples report are now safe. Now it looks like we need to go through that entire list of numbers on each line and tentatively remove one of them to see if the line then fits the criterion, and then we need to try that with every digit. But we also need to still accept ones that are safe without removing a level. Okay, so it looks like we still have the same criteria, we just need to apply these criteria to a different kind of sequence. We need to apply it either to the full sequence, as in this example, or to a sequence with one of the elements missing. So let's think about how we need to modify the program. So one essential part of this program is that after we've split each line of text by the spaces, so we now have the individual integers, except we're representing them as strings, then we're running it through basically this entire function, or this entire criterion, let's say, and then the result of that comes out here. So I think this will be most useful if I turn that into a function so that we can call it multiple times on multiple different inputs. So let's just split it off from the main program, and this function is going to have one input and one output. So I'm going to start by putting a declaration box at the top. And what should I call this function? Well, remember that in the second video, the second part for the day 1 challenge, we used a 1 in a circle. So I'm just going to use the same convention now and use a 2 in a circle because we're on day 2 now. But now the input points down, so we need the output to also point down. So I'm just going to change that over here. And now we have a self-contained function here, which we don't really need to worry about anymore. So let me just fix the program so that it uses the new function. And then let's check if the program still works by running it through the example input, which should give us a 2. And indeed it does. Okay, but now we no longer want to just run that function on the input sequence. We also need to run the function on all of the modified versions of the input sequence where we're removing one element at a time. So the new criterion that we care about is basically a Boolean OR, isn't it? It's either the original sequence or it is one of the modified sequences. So we're going to draw a Boolean OR the same way that we did last time with both of these not boxes. And let's move one of them over to the right so we have more space. Now the first one is literally just going to be calling this function. So I'm going to put that one on the far right because then I have more space in the middle to do the more complicated part. Okay, now let's move this down to make more space. So what do we want here? We want to check if any one of the possible variants of the sequence where one element is removed fits the criterion. Now you remember that our function here uses the for all function, which checks if every element within a sequence matches a criterion. Well, it turns out I also have a counterpart here, the exists function, which will return true, represented by -1, if any one element satisfies a predicate. Now the predicate in our case is of course this, so all we need to do is create a sequence of all the variants of the sequence and run each of those through that. So let's put a call to the exists function right here. And the thing that goes in on the left is the sequence of the variant sequences. So let's do that later. The criterion that we need to check against will be a lambda expression. So we're going to put a lambda expression box right here. So if that's where the lambda expression comes out, this is where the input comes out. And the input to the lambda expression in this case is one of the variant sequences. So we need to check that this variant sequence fits that criterion. And then the result of that needs to go here into the first output of the lambda expression. The second output of the lambda expression, well, the exists function doesn't care about it, so we're going to put a 0 there. Okay, looks like I didn't need to move that so far to the right, so let's just bring that back. Now let's think about what needs to go here. Remember, we're splitting at the spaces, so we end up with a sequence of strings, but the function that we have down here already does the conversion from strings to integers, so we don't need to worry about that. We can treat them as strings for now. And we're gonna need multiple copies of this, so I think I'm just going to put a splitter here now. So what we have here is the original sequence, and what we want to go in here is a sequence of the variant sequences. So let's think about how we're actually going to make them. Let's say you have an integer that specifies which element you want to remove from a sequence. Well, it turns out we already have a function for that as well, one that just omits or removes one element from a sequence that is identified by its index. And we want to do that with every element, so we need all of the indexes from 0 to the length of the sequence -1. So we're definitely going to need the length of the sequence, so why don't I just put a count right here? And then I want a sequence of increasing integers starting at 0, but this many of them. We have a function for that as well. It's right here. It's the toMusicalNotes function. We've had this in a previous video. Now, the second argument to the toMusicalNotes function is, of course, 0, which is the starting point for our sequence of integers. But the starting point is actually the first parameter, which means that in order for the order of these two to be correct, I need the output to come out on the left here. Now, for every one of these integers, we want to create a variant of this sequence in which that element is removed. And whenever you have a for each element in a sequence, well, you know what happens. Map is what happens. So to do that, we need to pass a lambda expression into the map function. So if that is where the lambda expression comes out, then this is where its input comes out. The input being one of the integers from our counting up sequence. And then this is the output of the lambda expression, which is where we want the variant sequence to come out. So this is the result of the omit function. So let's put the omit function here. The first argument to the omit function is the sequence, which is the sequence that we have up here, right? The original sequence of space-separated numbers. And the second argument to the omit function is the index of the element that we want to omit, which is the integer that comes out here. So we need to put a wire crossing function here. And now that we have a wire crossing function, we can just pipe the input from the lambda expression, which comes out here, into the omit function where we want it. And the second output to the lambda expression is something that we don't care about, so I'm just going to pass in a 0 there, which the map function is going to ignore. So now we have our sequence of variants coming out the bottom here, and we already know what we need to do with that. We need to run it through this to check if any one of them matches the criterion. And finally, the last copy of that original sequence needs to go in here so that we can check the unaltered sequence, the one that is not a variant. Okay, so this is what our program looks like. Let me include the function that we need for it so that you can see the actual size of this program. And now let's run the new version of that program with the example inputs, and we get a 4. And indeed the website says that it should be 4. 4 reports are actually safe. So now I'm going to run it on the full output, and I'm also going to use a time measurement so that we can find out how long it took. And it turns out it took 15.9 seconds. Now if you remember the first part of this day, it took 9 seconds, so our programs are getting more and more complex. Now let me paste the answer that I got into this answer box to check, and it turns out that is the right answer. So we have now solved 4 challenges, and so far they've been really interesting and really challenging. There is a lot of variety here. It's not getting monotonous. We have to keep thinking about how to do the new thing compared to the previous challenges. So I can't wait to see what the next challenge is. And I fully expect the challenges to only get harder and harder with every day, which in my book translates to more and more interesting. So, looking forward to day 3.